Thank you, everyone. And I'm Yuvaraj, currently a postdoc at University of Leeds. In today's presentation, I'll talk about uh, the understanding we had about calcined clay from the previous presentation and taking it further to look at the role of calcined clay on pore structure and thereon on transport properties and performances. I should acknowledge the work was done primarily as a part of my PhD, which was submitted last year. And I would like to thank other contributors, Professor Manu Sandhanam and Ravindra Gettu from IIT Madras. Moving on, this is a brief outline of my presentation. I'll try to set the context, talk about opportunities and challenges with calcined clay addition, briefly introduce the research matrix, and discuss the role of calcined clays in terms of its phase assemblage, physical structure development, and various techniques we use for understanding it, how we can link the parameters from pore network to transport properties, and some perspectives on how we can understand pore structure development with blended cements with calcined clay, followed by summary. So we know that calcined clay and limestone are two resources that are expected to grow from nearly 8% of the current contribution to about 25% over the next few decades. And it's also a material with extremely low level of emission factor, making it one of the very prominent and useful resources to produce sustainable low energy binders. Considering the fact that demand is expected to grow over the next few decades, and utilization of the wide range of clay will be a suitable route to produce cementitious material across different parts of the world. Clays can be used in several different forms. Direct addition of clays will bring in classical pozzolanic reaction, where you have benefits in terms of lower Portlandite and improved space filling due to pozzolanic CSH. Where it becomes more interesting is the use of clays in combination with the carbonate source like limestone dolomite or marble dust, whereas the reaction of the excess aluminate, especially from calcined kaolinite based clays, with the carbonate produces the carbo-aluminate hydrate phases, where the additional benefits from limestone like acceleration of clinker reaction, stabilization of ringites, along with the reaction of carbo-aluminate phases, produce a very diverse phase assemblage, which produces interesting performances in cementitious system. So we try to look at it into three scheme of work. Try to look at chemical interaction in terms of binder composition, ingredient characteristics, understanding the kind of impact it has on phase assemblage, characterize the physical structure in terms of porosity, pore sizes, and pore connectivities, and try to link it up to explain performance in terms of transport properties, so we can establish structure property relationships in this material, so that when we start accommodating a wide range of different resources, we need not go through the entire scheme of work for all the materials. So this is the matrix that we try to use, a plain Portland cement, 5 different SCMs, the calcined kaolinite based clays with about 55% kaolinite content. We had 3 different fly ashes because there's a lot of variability with fly ashes. So 2 siliceous fly ash and 1 calcareous fly ash and a slag, and a limestone with about 42% calcium oxide content. The dosage of limestone was varied up to 20%, and these are the formulations of binary and ternary systems that were used. So the mixed design for cement paste and the concretes that will be discussed in the further slides. A water binder ratio of 0.4 and concretes to produce a slump of about 100 mm with this mixed design. Looking at why we need to focus on the role of physical structure and transport properties is when we look at the blended systems, especially the transition from high volume pozzolanic admixture based systems to a combination of fly ashes or calcined clays with limestone, you don't produce significant variation in strength. There are some minor differences, but where we do see a major differences in terms of durability performances. So as you can see, these are chloride penetrability and moisture ingress. The impact of dilution from limestone addition is visible directly with fly ashes, whereas with calcined clay, you have significantly lower chloride penetrability and quite consistent moisture ingress. So there is a major difference in these parameters which need to be explained in terms of its microstructure development and pore structures, other than on the compressive strength as such. So trying to set what is the kind of interaction we look between just clay and clay limestone combinations. So these are ternary systems with 10% and 15% limestone, we see about 5 to 25% of these carboaluminate-based AFM phases can form in the systems. Clays, along with slag and the calcareous fly ashes, had a higher amount of carboaluminates with both limestone dosages compared to the siliceous fly ash. Now, the question is formation of these phases at the expense of pozzolanic CSH beneficial in terms of post-structure development? And what are the roles of these alteration on the development of microstructure as such? So in the beginning, we tried to use MIP to characterize the pore structure, which is very widely used. As you can see, this for a fly ash system and a calcined clay-based system. We have a highly refined pore structure with calcined clay as early as 7 days compared to Portland cement and fly ash-based binder. But where we don't see much difference is with age, the kind of evolution that happens with microstructure is not quite well captured with the MIP. So there is very limited change from the MIP curves for calcined clay systems across ages. So we resorted to other forms to monitor the physical structure development using the formation factor approach. Whereas this is for fly ash and fly ash limestone combination, you have a higher formation factor values for ternary systems with limestone addition at early ages. And there onwards, high volume fly ash continues to grow, evolve, and reaches high value at 400 days. The transition happens for both binary and ternary systems at almost similar ages compared to TC. This for the calcareous fly ash, which had higher amount of reactive alumina and carboaluminate phases. You have a synergistic rise in the ternary systems with the fly ash limestone combination up to 14 days, and there onwards it follows a very similar trend compared to binary systems. This for slag system, salt slag system, rise between 3 to 7 days, and this is the kind of development we get from ternary, binary and ternary systems with calcined clay. We have a major rise between 1 to 3 days, and there onwards it continue to evolve even up to 400 days quite slowly. So IF formation factor means that we have a lower porosity and the connectivity states of the pores are also lower. So now this has a direct implications on the durability performance as such. So when we try to look at transport performances, so this is for fly ash and fly ash limestone combination. The binary systems have a lower moisture ingress profile and absorption rate compared to the ternary systems with limestone, which has a higher absorption due to the dilution from limestone addition. In the case of calcined clay, due to the dense microstructure that's formed in the system, both in binary and ternary systems, even the ones containing up to 20% limestone have lower sorptivity profiles. This is mainly due to the early development of microstructure that was captured in the previous approach using formation factor as I presented. Moving into whether we can explain the performance of concrete using this parameter. So we try to relate it with different microstructure-based factors. For example, when we look at chloride penetrability rate and moisture ingress rate with porosity, you do see a generic trend, but the scatter is quite large at a fixed given porosity. You have a very wide range of transport indices that can be obtained in the system. Well, the use of formation factor can give a much better trend to explain both chloride transport in saturated concretes and moisture ingress in unsaturated concretes. So with all the intricacies that could be present due to mixture proportioning and binder chemistry, do feel that formation factor captures the physical state of the cementitious system much better with respect to its transport performances. So we tried to decouple the effect further, take up this porosity and pore connectivity and estimate it in terms of the tortuosity parameter. And when we try to plot it, it follows a trend which is close to the tortuosity-based diffusion formulations presented in porous media literature for others materials. So we do feel that tortuosity as a pore network parameter explain the kind of improved chloride resistance that we see with calcined clay formulations across a wide range of binary and ternary formulations. We try to purposefully make some calcined clay concretes with higher porosity, and all that it could end up was here. So we, because of the dense pore network and highly tortuous porosity, it is always expected to have a very low transport characteristics like chloride penetrability. Of course, there are other parameters which also has an impact. And when we try to look at it, it showed very limited trend compared to the core network-based parameters as such. We try to understand the evolution of this parameter further by relating it to pore sizes. So when we try to look at when the pore sizes in the early ages were in the order of few hundreds of nanometer, there is a gentle rise in the formation factor value. But once it reaches a range of about 10 to 30 nanometers, there is a major rise. So we attributed this as a densification regime, wherein in the regime 1, you have porous outer CSH spreading to reduce the interparticle space. And there onwards, once it reaches a narrow range of 10 to 30 nanometers, there is significant depercolation that occurs, which makes the pore network highly tortuous, leading to major rise in formation factor in both paste and concrete systems. So why does it occurs, and what causes, what are we missing in the MIP curve is the volume corresponding to the critical pores. So you compare at 90 days binary and ternary systems with clay, you have almost similar critical pore sizes, but the volume of pores corresponding to the critical size range varies. The one with the lowest volume of pore has the highest formation factor. And even with age, we see a limited change in the critical pore size, which is widely used from MIP as a parameter. But the difference is more clearly seen in the volume corresponding to the critical pore size, which continuously reduces from 28 to about 180 day. And this is quite clearly captured and reflected as increased formation factor with ages in the same system. To summarize, we see a limited difference in strength, even up to 20% limestone addition with calcined clay, so which makes it suitable to use high volume substitution with clay and limestone in combination. General alterations in durability parameters are more significant compared to strength, and the dilutions are visible in fly ash limestone combination and not necessarily in calcined clay limestone combinations on the durability parameter. Choice of SCM controls the amount of carboaluminates that is formed. We see both slag and calcined clay forming a higher amount of these carbonate AFm phases from the alumina in these systems compared to fly ashes. And what we also see is these has to be supplemented by pozzolanic CSH, because all the formation factor trend clearly showed that both binary and ternary systems follow a similar kinetics of physical structure development with and without limestone. Formation factor and tortuosity at pore network parameters explain the transport behavior in this range of different binder chemistries. And we do see that reactivity of the system, which impacts the kinetics of physical structure development, is almost similar in both binary and ternary systems. And the twofold structure development mechanism was conceptualized. There is convergence of hydrates, which happens quite rapidly in the case of calcined clay systems. There onwards, there is a densification of physical space, which is governed by kind of other factors that could lead to slower development of microstructure over the curing period. With this, I would like to bring everyone's notice to the Gordon seminar that we are hosting in February next year. So I'd like to invite everyone to submit your abstract and participate in the conference. Thank you for listening. I would like to acknowledge funding sources which funded my PhD work, and I would also like to acknowledge RENSM project for sponsoring my participation in the conference. Thank you.
Thank you, Yuvaraj. Well done and comprehensive work. Oh, well, there's a question. Are diffusion coefficients available for this work?
Yes, we do have the diffusion coefficient for not all of the concrete, but for some of the concretes which were presented here. And I can share the reference to that in the answer.
Okay, thank you. Thank you so much, Yuvaraj.